AC circuits are like the heartbeats of our electrical world. Instead of a steady flow, the current in an AC circuit changes direction constantly. Think of it like waves in the ocean, constantly ebbing and flowing. This back and forth movement is what makes them different from DC circuits, where the current flows in only one direction. These AC circuits are everywhere, powering our homes and our gadgets. They are essential for running motors, lighting our lamps, and even powering our computers. From the power grid to our smartphones, AC circuits are the backbone of modern electrical systems. Now imagine pushing a child on a swing. If you push at the right rhythm, matching the swing's natural frequency, the swing goes higher and higher. This, my friends, is resonance. In AC circuits, resonance happens when the frequency of the AC source matches the circuit's natural frequency. This special frequency is called the resonant frequency. At this frequency, something amazing happens. The circuit starts to store and transfer energy back and forth between the inductor and capacitor. Just like the swing going higher, the current in the circuit at resonance can also reach very high values. There are two main types of RLC circuits where resonance plays a crucial role: series and parallel. In a series RLC circuit, the resistor, inductor, and capacitor are connected one after the other. Here at resonance, the impedance of the circuit is at its minimum, allowing maximum current to flow. On the other hand, in a parallel RLC circuit, the components are connected in parallel branches. At resonance in a parallel RLC circuit, the impedance is at its maximum, leading to minimum current from the source. This difference in behavior between series and parallel resonance is important for various applications. Resonance is not just a theoretical concept, it's the magic behind many everyday devices. Take radio receivers, for example. They use resonance to select a specific radio station. By tuning the circuit to the frequency of your favorite station, you allow that particular frequency to be amplified. Filters, used to remove unwanted frequencies from signals, also rely on resonance. They are essential in audio systems, telecommunications, and even medical equipment. By understanding resonance, we can design filters that allow only the frequencies we want, making our technology work better.